magnetic materials. First question, page number 263. When a plate of magnetic material of size 10 centimeter into 0.5 centimeter into 0.2 centimeter. So in the question, they have been given the dimensions. Whenever there are dimensions given, so here they have mentioned that it is length, breadth, and height, thickness, which is given. Length, breadth, and thickness is given. So that means we can say it is a volume which is given to us. So length, breadth, and thickness is given. That means volume 10 centimeter, length is 10 centimeter, breadth is 0.5 centimeter, and the thickness is 0.2 centimeter. Is located in a magnetizing field of 0.4 into 10 raised to 4 ampere per meter. So let us write the given data first. We have been given the volume of the particular magnetic material is given. So this is the volume. 10 centimeter into 0.5 centimeter into 0.2 centimeter. The volume is given 10 into 0.5 into 0.2 centimeter cube. So 10 into 0.5 will be 5. 5 into 0.2 will be 1. So that will be 1 into 10 raised to minus 6 meter cube. I have converted centimeter cube to meter cube. So centimeter cube is 10 raised to minus 6. So the volume given is 1 into 10 to the power minus 6 meter cube. This is given to us in the question. Then they have also given one more thing is given to us, that the magnetizing field, always remember magnetizing field is denoted by H. So H is given, magnetizing field is H, that is 0.5 into 10 raised to 4 ampere per meter. Then magnetic moment is given M, that is 0.5 ampere meter square is given to us, is induced in it. Find the magnetic induction. Magnetic induction means B is supposed to be found out. Now we know that B is equal to mu 0 magnetization mz plus H. I'm denoting magnetization by mz, and magnetization formula is magnetic dipole moment per unit volume plus H. So this will be our formula. The magnetic field induced will be equal to mu naught bracket magnetic moment small m divided by volume capital V plus H. Mu naught is a constant value. Mu naught value is 4 pi into 10 raised to minus 7 in SI units. This value is supposed to be remembered. In magnetic field chapter, we have done this particular value. So B will be equal to mu naught is 4 pi into 10 raised to minus 7. M is magnetic moment, that is 0.5 upon volume is 1 into 10 raised to minus 6 plus H value is 0.5 into 10 raised to 4. Now what let us do here, this will become 12.56 into 10 raised to minus 7. I can write this as 0.5 into 10 raised to 6 plus 0.5 into 10 raised to 4. This can be written like this: 0.5 into 10 raised to 6 plus 0.5 into 10 raised to 4. So when you solve this value, 0.5 into 10 raised to 6 plus 0.5 into 10 raised to 4, you see here the 10 power is not same. In addition, the rule is the 10 power should be same. So let us first make the 10 power same. So here keep it as 12.56 into 10 raised to minus 7. I will make this 0.5 into 10 raised to 6 as 50. 50 into 10 raised to 4 plus 0.5 into 10 raised to 4. I have converted 10 raised to 6 to 10 raised to 4 because whenever there is an addition of 10 power, we should always make sure that the 10 power is same whenever the 10 power is same. So now in this case you can see both terms in the addition are having 10 raised to 4, that is same. Now you can directly add, that is 50 plus 0.5. 50 plus 0.5 will be 50.5 and 10 raised to 4 will be taken common, right? So always you have to please make sure in your bracket term the 10 power should be same. When until your 10 power is same, you cannot add. Same goes with subtraction also. We cannot subtract the numbers if we don't have 10 power as same. So here you can see I have made both 10 powers as 10 raised to 4. I can take 10 raised to 4 common, and addition of 50 and 0.5 will be 50.5, and the final answer I will get will be 6.286 Tesla. 6.286 Tesla, right? Next. A rod of magnetic material of cross sectional area is given. I have been given the area as 0.25 centimeter square. Converted to meter square, that will be 0.25 into 10 raised to minus 4 meter square. Placed in a magnetizing field, again magnetizing field means H, that is 4000 ampere per meter. The magnetic flux denoted by phi is 25 into 10 raised to minus 6 Weber. Find out the relative permeability, that is mu r. Find out the magnetic susceptibility chi, and find out the magnetization mz. Before I find these things, I will have to find the magnetic field, because magnetic field formula will be required here. So magnetic field is flux upon area, magnetic flux upon area. So I can write magnetic flux upon area as 25 into 10 raised to minus 6. I can rewrite this area as 0.25 into 10 raised to minus 4 can be written as 25 into 10 raised to minus 6, right? So this can be converted in this 10 power. Those students who fail to understand how do you convert this 10 power, you can watch another video. I have made one video on basic conversion of 10 powers. Please go through that and understand how do you convert the 10 power numbers. So this can be written as 25 into 10 raised to minus 6. So you see both are getting cancelled. So that will 1 Tesla. So the magnetic field is 1 Tesla. Now I can find the value of relative permeability and others. So the first case that I will be using is to find mu r. So I know mu equal to mu 0 into mu r. This formula is known to us. And why I'm using this? Because we know B equal to mu h. So I can write B equal to, instead of mu, I will write mu 0 mu r into h. And mu r will be equal to B upon mu 0 h. So just substitute the values over here. Please remember the value of mu 0, that is a constant, 4 pi into 10 raised to minus 7. In SI units, this is the value. That is a constant value. You substitute the value, you get the value for mu r. So mu r will be 199. When you substitute the value, you get the mu r as 199. Next value is susceptibility. We know the relation between susceptibility and mu r. Mu r is 1 plus chi. So I can write from here chi will be equal to mu r minus 1. So I just need to subtract 199 minus 1. So that will be 198. Chi will have no unit. Mu r will also have no unit. Chi will also have no unit. They both are unitless quantities. Next, I have magnetization. Third case. Magnetization mz is chi into h. So chi is 198 into h is 4000. So when you solve this, you get 792 into 10 raised to 2 ampere per meter. That will be your answer. Okay, this will be 792 into 10 raised to 3. This will be 792 into 10 raised to 3 on solving this. Next up, the work done for rotating a magnet with the magnetic dipole moment m through 90 degree. The first angle is given as 90 degree. So let us write this as theta 1. Let us assume theta 1 is given as 90 degree. From its magnetic meridian is n times the work done to rotate through 60 degree. So this has been second angle given. Let's theta 2 is 60 degree. Find the value of n. I need to find the value of n. I repeat once again. The work done for rotating a magnet with magnetic dipole moment m through 90 degree from its magnetic material. We assume the magnetic meridian is on the axis of the bar magnet. So suppose if I draw a pictorial representation, this is a bar magnet, north pole, south pole. This axis, this is called as axis. This is called as axis, and axis is considered to be as a magnetic meridian. So the magnetic meridian is given to be as an axis. Now axis where the angle will be 0. This is a 0 angle. This is a 0 angle. So I will say theta 0 is 0. So from 0 to 90, it has been done. There will be some work done to rotate it from 0 to 90. The work done is told. So let it be W1. Let W1 be the work done. Let W1 be the work done to rotate a bar magnet through 90 degree. Through 90 degree from which point? From its magnetic meridian, that is 0 point, right? From its 0 point. So we know that the work done formula, work done will be equal to mb into cos theta 0 minus cos theta 1. This is our formula. I'm writing W1 over here because the first work done. So W1 will be equal to mb into cos 0 minus cos 90, right? So W1 will be equal to mb into 1 minus 0. That will be mb. So the first work done which I've got from 0 to 90 degree will be mb. M is magnetic dipole moment mentioned in the question. B is magnetic field. So the first work done will be W1 equal to mb. I repeat once again, magnetic meridian will be considered as a 0 degree angle. So the first question says that the work done for rotating a magnet with magnetic dipole moment m through 90 degree. From where it is rotated? From magnetic meridian. Matlab it is going from 0 to 90. Next, the question says, is n times the work done to rotate through 60 degree? The same thing when it is rotated by 60 degree. So let us assume that W2 will be the work done. Let W2 is the work done. in this case, to rotate it through 60 degree. Again, it is rotated through 60 degree using magnetic material only. So you will have to consider the first angle as 0 only. The first angle will be 0. From magnetic meridian, it is rotated through 60 degree. So let W2 be the work done to rotate a bar magnet by 60 degree from magnetic meridian. So W2 will be equal to MB cos theta 0 minus 60 I have taken as theta 2. So I'll write it as theta 2. So W2 will be equal to MB into cos 0 minus cos 60. So this will be equal to MB into cos 0 is 1, 1 minus 1 by 2. 1 minus 1 by 2 is 1 by 2. So this will be MB by 2. Give it as equation 2. Let this be equation 2. From 1 and 2, I can write W2 equal to W1 upon 2. Why? Because if you see here, MB is W1, right? If you see here, MB is W1. Since MB is W1, I can rewrite MB over here as W1. Here I'm substituting at W1. So what do I get? W1 equal to 2 times of W2. So what is the N value? W1 equal to N times W2. So N is 2. The value of N is 2, twice. Next question, an electron in an atom. This is a very important question. This is a previous year question asked in board exam. An electron in an atom is revolving around the nucleus in a circular orbit of radius is given 5.3 into 10 raised to minus 11 meter. With speed v is given 2 into 10 raised to 6 meter per second. Find the resultant orbital magnetic moment m and angular momentum L. The constant values are given. Very simple sum. Magnetic moment for hydrogen atom in case because electron is revolving around the nucleus will be given by EVR upon 2. So magnetic moment is E. E is the charge of electron that is given to us in the question. 1.6 into 10 raised to minus 19 into velocity 2 into 10 raised to 6 into 5.3 into 10 raised to minus 11 divided by 2. So when you solve this, you get the answer as 8.48 into 10 raised to minus 24 ampere meter square. That is your answer. Next one, they are asking angular momentum. To find angular momentum, we know that gyromagnetic ratio. Gyromagnetic ratio definition we have. Gyromagnetic ratio is M upon L. So gyromagnetic ratio is 8.8 into 10 raised to 10. That is equal to M value, which we have got 8.48 into 10 raised to minus 24 upon L. So from here I can write L equal to 8.48 into 10 raised to minus 24 divided by 8.8 into 10 raised to 10. So when you solve this, you get the angular momentum 9.65 into 10 raised to minus 35. That is your answer. Next, a paramagnetic gas has 2 into 10 to the power 26 atoms per meter. Let us assume the number of atoms which are given as n. Let this be n. N atoms are given. That is 2 into 10 raised to 26 atoms per meter with atomic magnetic dipole moment. With atomic magnetic dipole moment, that is say small m, that is given to us as 1.5 into 10 raised to minus 23 ampere meter square. This is denoted by small m. The gas is at temperature is given 27 degrees Celsius. Find the maximum magnetization intensity of the sample. So maximum magnetization. Now this is a new formula. You will have to remember the formula. The maximum magnetization intensity is given by M max is equal to M max is maximum magnetization is dipole moment into number of atoms. This is the formula. This you will have to remember. You have to just multiply the two terms. So you get M max will be equal to 1.5 into 10 raised to minus 23 into 2 into 10 raised to 26. So you get this 3 into 10 to the power 3. The maximum magnetization, you will get 3 into 10 to the power 3 ampere per meter. This will be the maximum magnetization. The second question is saying if the gas is in this problem, if the gas in this problem in this question is kept in a uniform magnetic field of 3 Tesla, is it possible to achieve a saturation magnetization? So magnetic field is also given, B is given 3 Tesla. So if let us convert the 27 degrees Celsius, this will be 300 Kelvin. So if the maximum magnetization we have already got, that is 3 into 10 to the power 3. So you see the maximum magnetization is 3 into 10 raised to 3 into 10 raised to 3 means 3000, right? 3000 ampere per meter. Magnetization we only get from magnetic field. Magnetization is a property which we get from magnetic field. In the question is saying we have a magnetic field of 3 Tesla. But how much magnetization we are getting? 3000 magnetization, which is very, very much larger. So is it possible to achieve saturation magnetization? No. So the answer for second question is no, it is not possible to achieve so it is not possible to achieve saturation magnetization. Why? Because you see the magnetic field value is very, very less as compared to magnetization value. So M max is very, very greater than B. Hence, it is not possible to achieve saturation value. 3 Tesla is very, very smaller as compared to the 3000 value. So that is not possible to achieve a saturation value. A magnetic needle uniform magnetic field displays a uniform magnetic field as magnetic moment. Magnetic moment denoted by small m. Magnetic moment is given to us in the question. That is 2 into 10 raised to minus 2 ampere meter square. The moment of inertia I is given 7.2 into 10 raised to minus 7 kg meter square. Number of oscillations is 10 in 6 seconds. Number of oscillation is 10 in 6 seconds. So number of time period for one oscillation will be 6 by 10. 6 oscillations are performed in 10 seconds. I need to find for one. Time period is the time taken for one oscillation. So you need to find the time taken for one oscillation. So you divide it by 10, 6 upon 10, that will be 0.6 second. What is the magnitude of the magnetic field B? So we know that T equal to 2 pi root I upon MB. So just square this term, squaring this equation. So you get T square equal to 4 pi square I upon MB. And therefore you get M equal to, sorry, you need to find B. So B is equal to 4 pi square I upon M into T square. So just substitute the values. On substitute the value of 4 pi square I M T square, you get 39.48 into 10 raised to minus 4 Tesla. This is the magnetic field value. A short bar magnet is placed in a magnetic field of 700 Gauss. So you have been given the magnetic field is given 700 Gauss. Converted to Tesla. So 700 into 10 to the power minus 4 Tesla. Remember, 1 Tesla is 10 raised to 4 Gauss. There is a conversion. 1 Tesla is 10 raised to 4 Gauss. There is a conversion. I'm converting Gauss to Tesla, so that will be 10 to the power minus 4. When its axis makes an angle of 30 degree with the external magnetic field. So it is given in the question, the axis is making an angle theta with the magnetic field, that is 30 degree. And it experiences a torque of 0.014 Newton meter. Torque is given, angle is given. So I'll write that. So theta is given 30 degree. Torque is given 0.014. Let me write this as 14 into 10 to the power minus 3 for easier calculation. Find the magnetic moment M. I'm supposed to find M. And the work done in moving from most stable to most unstable position. Work done. Always remember, most stable position is theta equal to 0 degree, and most unstable position is theta equal to 180 degree. Always remember these two things. Most stable position is 0, most unstable position is 180. First, let us find the magnetic moment. So torque is given tau equal to mb sine theta. So m will be equal to tau upon b sine theta. That is 14 into 10 to the power minus 3 divided by b value 700 into 10 raised to minus 4 into sine 30, that is half. Right? So when you solve this, you get magnetic moment. So the answer for magnetic moment in this case will be equal to 0.4 ampere meter square. Second case, the work done will be equal to mb cos theta 0 minus cos theta, the formula which we had used earlier. So W will be equal to M will be this 0.4. 0.4 into 700 into 10 to the power minus 4 into cos 0 minus cos 180. Cos 0 value is 1, cos 180 is minus 1. So this will become 2. So this will become 2 into 0.4. 1 minus minus 1. That will be 2. 2 into 0.4 into 700 into 10 to the power minus 4. So when you solve this, you get 0.056 joule. That's the answer. A magnetic needle is suspended freely so that it can rotate freely in a magnetic field, in a magnetic meridian. In order to keep it in horizontal position, a weight of 0.2 grams. So weight is given to us as 0.2 gram. Whenever the weight is given, you have to convert it to Newton, because weight unit is not in grams, weight unit is in Newton. So weight equal to 0.2. You have to convert that gram. Gram is 10 to the power minus 3 kg, and you need to convert it to Newton. You multiply by 9.8. Always remember, students, whenever weight word is used, you have to convert it to Newton. You convert weight to Newton by multiplying by 9.8. And since here gram is given, I have converted gram to kg by multiplying by 10 to the power minus 3. So the 10 to the power minus 3 indicates I have converted from gram to kg, and the 9.8 indicates I have converted it to Newton. So you can just keep it as it is, or you can just solve. So this will become 1.96 into 10 to the power minus 3 Newton, kept on one end of the needle if the pole strength of the needle is 20 ampere meter. Pole strength is denoted by P. P is the pole strength that is given by 20 ampere meter. Find the value of the vertical component of the magnetic field. B. I am supposed to find the vertical component of the magnetic field. Whenever pole strength is given, there is a relation from 11th standard textbook that we have learned that magnetic moment is small m, that is pole strength, that is P into 2L. 2L is the distance between the two poles of the magnet. I know this formula. Now we know this relation, right? Give it as equation 1. We will use this relation. Now, since it is will be at equilibrium, it is in order to keep it in a horizontal position. That means it will be in equilibrium. So the restoring force is equal to the torque produced by the needle. So at equilibrium position, the torque produced by the needle should be equal to the restoring force. And for that, restoring force means weight that we will have, right? So that will be equal to, torque will be equal to, so here using this equation, I can write torque, that is L into F, should be equal to the restoring force, that is M cross B, right? So both are torque equation. So I can write L into F can be written as weight. F can be written as weight, that is 1.96 into 10 to the power minus 3 into equal to magnetic moment. That is magnetic moment is this formula, pole strength into 2L. So I'll write it as pole strength is 20 into 2L into B. So you can see L getting cancelled from both sides. So I can write B is equal to 1.96 into 10 to the power minus 3 upon 20 into 2. Here there is 2L, right? 2 is left out over here. So when you solve this, you get the magnetic moment as 4.9 into 10 to the power minus 5 Tesla. Little tricky sum, but a good question to solve. Last question for the chapter. We have been given a susceptibility of a paramagnetic material chi at 27 degrees Celsius. So let chi1 is equal to chi. Let T1 is 27 degrees Celsius, that is 300 Kelvin. Convert it to Kelvin. At what temperature, second temperature has been asked, will the second susceptibility chi by 3? So we know that for paramagnetic substance, chi is inversely proportional to temperature. So I can use chi1 upon chi2 equal to T2 upon T1. This will be my formula. So I have been given the three values. Rearrange. So T2 will be equal to chi1 into T1 upon chi2. So T2 will be equal to chi into 300 divided by chi by 3. Chi cancel. 3 will go up, that will become 900 Kelvin. Keep it in Kelvin only. We need the answer in SI unit. So Kelvin will be the unit for SI unit of temperature. So the second temperature is 900 Kelvin. So this was for magnetic material.